So let's make a start. So today's speaker is Tom Bland, and he's going to tell us about some exciting new theoretical and experimental results on supersolidity in a circular trap. So please, when you're ready, Tom, just take it away.
Cool. Thanks, Andrew. Yes, so I am talking to you today from here. So I moved to Innsbruck last year. I was in Newcastle actually for 10 years, undergrad, master's, PhD, postdoc, and then finally moved away to the Alps. And my house is somewhere behind this tree, I think. I was trying to find it earlier. And the lab is over here. So here is a picture of something I don't understand as a theorist, but this is the erbium dysprosium lab they have here. So there are two labs that have, or at least within Francesca Falena's group, there are two labs that deal with Bose-Einstein condensation. One of them's purely erbium, and the other one can do either erbium or dysprosium or mixtures of them both. And so this was for the new results over the last few years, be the first group to do dipolar mixtures. But one thing I was looking at this earlier, trying to see if I have had a lab tour, see if I can remember anything useful to say. But I did notice that there's this box here, which I know to be from a box of lab snacks. I know a lot of laboratories around the world have, and it's just sellotaped to this. So I'm sure it's very important and we shouldn't touch it. But I just love the idea. It's just something's been patched up with sellotape with a cardboard box. But yes, so this is where the magic happens. Somewhere over here. And okay, so I'm going to talk to you today about supersolidity. So I'm going to take the idea that you are familiar with superfluidity and just build on that for those that haven't come across supersolidity before. So the definition to have in mind for the entire talk is it's a quantum fluid that has the crystalline order of a solid, but the frictionless flow of a superfluid. So initially, the first works, well, this is back in 1956, actually said that this wouldn't be possible. So this is a paper from Penrose and Onsager. Maybe you won't be able to read what's highlighted in the abstract here, but it says, conversely, it has shown why one would not expect BE condensation in a solid. So the idea being that if you have this delocalized object, the superfluid, right, you have like a phase coherence across this whole system, and a very localized idea of something being solid and having some crystalline structure, that these two shouldn't be able to compete with one another, shouldn't be able to coexist, with one another. But then just 1 year later, and for the rest of time, there's been many papers that disagree with this idea. And so initially from Gross in 1957, and then this idea of this land of Andrew, Lifshitz, Chester, and sort of solid. So these papers, these original papers, more had the idea that you can have a solid, this is all focused mostly on solid helium, and then you have a defect in that solid, and this defect will move around. So this hole in your solid will move around the solid frictionlessly. So in this sense, it's moving like a superfluid. And so it's really building this idea that you can, the question really is, can a solid be superfluid? And that's the title from Leggett's paper here is. And this question was kind of, it's been floating around, obviously, for, can't do maths, 50, 60 years. And the answer originally back in 2004 was yes, very. And there's this probable observation of supersolid helium phase in this really nice experiment in liquid helium. And then this birthed a lot of papers trying to understand these observations from this work, and other experiments trying to reproduce the observations of this work, and no one could. But in the theoretical foray that followed, there was a lot of really nice new methods of testing supersolidity that were born from everyone desperately trying to understand what had been observed. And in the end, actually, it was the same authors who came along and realized that actually it wasn't supersolidity. In fact, it was the observation they had was something more to do with the elastic properties of solid helium. And this wasn't originally accounted for, but when it was, actually found their observations could be explained by a different mechanism. And ever since then, and obviously also at the time, the converse question has been asked. So can a superfluid be solid? So could you have some Bose-Einstein condensate, which then gains in some manner some crystalline order? And all of these names, and there's many more that I haven't written here, have all contributed to the sort of theoretical side of understanding this behavior and this phenomena of superfluid having some solid crystalline properties. And one ingredient that you require is you need a K-dependent interaction. And so here's just a few examples of systems that have that property. So Rydberg gases, and they also have exceptionally strong dipole-dipole interactions. Soft core interacting gases, so you have van der Waals interactions with a 1 over r to the 6 kind of potential is an example of one of those systems. Dipolar quantum gases, and the last two have coupled to sort of cavity modes. You have these K-dependent interactions. And actually, back in 2017, both of these systems, one by Esslinger, by Ketterle, were observed to exhibit this supersolid behavior. However, this was a perfectly rigid supersolid. So the crystalline shape was imposed externally or by these light-coupled interactions. And so you can't have phonons in this mode, which is another sort of property of superfluidity. You can't have that this crystal compresses and oscillates in any way. It's just an enforced structure. And so today I'm going to talk about dipolar quantum gases, which are so far the system that has shown both this supersolidity property, but without any enforced periodic structure. So I'm just going to introduce some of the ideas of, some of the other ingredients we need for this system. So this is the dipole-dipole interaction. So it's anisotropic. So here's like two dipoles placed at some angle theta. It's long range. So for the length between them scales as 1 over distance cubed. And its magnitude depends on this Bohr magneton, or this permanent dipole moment, which is proportional to Bohr magneton. And so this is a constant that depends on the species of atom you're using. So today I'll be talking exclusively about dysprosium, which has the strongest permanent dipole moment of all the rare earth metals. And so you could define from this like a dipolar scattering length. So this again is just going to be a constant. So for the dysprosium gases we discussed today, this is about 130 Bohr radii, right? If that means anything good. And also be utilizing but not talking much about this parameter EDD, which is the ratio of the long-range interactions to the short-range interactions. So one thing you do need is you need dominantly dipolar interactions. So we consider ADD greater than the scattering length, AS. So the Fourier transform of this interaction potential depends on K, although this is the angle in K space. This is kind of dependent maybe on your polarization. All your dipoles are considered to be polarized on one axis. But really, the real ingredient you need to have these K-dependent interactions also includes, let's say, it's like an effective potential. So it's all of the interactions put together, which will also depend on the trap, especially with these dipole-dipole interactions. So if you have like a cigar shape trap, and you have your dipoles polarized along the cigar, then you can have dominantly attractive dipole-dipole interactions. Whereas if like a pancake trap, or your little bar magnets are sat next to each other, and you have dominant repulsive interactions. So this effective dipole potential depends fully on K. And so the last thing you really need for dipole systems to have the right ingredients is this K-dependent interaction. Just open this chat. Okay. So this is point 1. The next ingredient for our recipe is you need some sort of instability in order to instigate this crystallization. So this here is the dipole, is the, I lost my train of thought, sorry. I have a few messages in the chat. Okay, sorry. Right. Is the excitation spectrum for this system. So actually this is general, this is how you would write the excitation spectrum for even an S-wave BEC, but now our interaction potential depends on the dipole-dipole interactions and is K dependent. And so if you plot this potential for the right parameters in the DDI, you have this Fernon branch. So you have the linear excitation spectrum. If this is non-dipolar, this would go off as K squared, just be free particle-like. But in dipole systems, you have this turns back around and has this roton minimum, and then goes off as free particle-like K squared. This roton minimum can be tuned, so the actual position of this minimum depends on actually the Z. Let's say we have dipoles along Z, you've got this sort of pancake system. It depends on the Z trapping. It tells you exactly where this roton's going to be. But by tuning this scattering length, you can decrease this minimum down to 0, and then you have, if you go below 0, you have this imaginary part, and so you have the unstable explosion of rotons in the system, and you have this collapse. So the roton spectrum was measured actually here in Innsbruck a few years ago now, and so they actually did Bragg spectroscopy, so you shine a laser specific spatial wavelength for a specific moving specific rate for the time. So you have some time dependent h bar omega. And then you repeat this for the entire 2D plane, and you measure the response after this perturbation. And this is what this structure factor is, this dynamic structure factor. So if you have a large response, then you're exciting exactly on this excitation spectrum. If you have no response at all, then you're not resident with the excitation spectrum. You get a black dot back. And so by decreasing the scattering length and then running a whole series of this Bragg spectroscopy, you can see exactly this roton minimum decreasing. Okay, so why does this lead to crystallization? If you have a specific momentum, K roton, this pertains to some wavelength, 2 pi over that momentum. Let's say you can excite just this one mode and this mode only, then this excites some density oscillation with a specific wavelength, for example, something like this. So you have your background BEC, and you have some density oscillation on top. And you can see this in the experiment by doing a time of flight image. So in the long time of flight, the density should resemble the Fourier transform of the wave function. And so from the superfluid part, you just get this macroscopic occupation of the K equals 0 mode. But for the density oscillations, you get peaks at plus and minus K roton, which are exactly because of the wavelength of the density oscillations. And this was seen in experiments a few years ago by just exciting the roton and then expanding the gas, and you can see these density oscillations. And so you have some peaks either side of the central main peak. Okay, so if that was all of a picture, the problem here would be that you pass through this unstable roton mode, you have an exponential growth of these rotons, and then you just have a periodic collapse of your density into huge spikes, separated out by this roton. So you need something to arrest this collapse, and this is the final ingredient that we require, is stabilization against collapse. And again, almost like serendipitously, dipolar gases have this, have exactly this, and this is due to the first order sort of correction from the S-wave scattering, which is given these quantum fluctuations. This is known about since 1957 for non-dipolar gases, where this function f of EDD, I won't go into too many details, but this would be equal to 1 for non-dipolar gases. But what's important here is this contribution scales as the density of the 3 halves. So when a density is small, this is completely negligible, and this is why it plays no role in most day-to-day BEC experiments. But during this collapse due to the roton, the density shoots up, and then this term kicks in. And this is a repulsive contribution to the to the mean field interactions, and then therefore it causes some arrest for this collapse. And so this was seen unknowingly in experiments, actually, first in 2016 from Till and Faust group, where they quenched the scattering length through this roton instability, and they created an array of this crystal, many droplets in this crystal, but they moved the scattering length too low. And so actually each one of these droplets has phase coherence across the droplet, but has a different phase to its neighbor. And so you don't have this property of global phase coherence that we want to call something a supersolid. And in the same year as well, here in Innsbruck, they did a similar experiment where they quenched the scattering length down, but with their parameters, the ground state configuration is just a single droplet. So this is actually turn off the trapping in free space. This is a bit like a 3D bright soliton, right? And it just stays stable in free space. So this was the final ingredient essentially, and it's just nice that it appears for us in these dipolar gases. So, okay, I know there's maybe quite a lot of information there, so I'm just going to basically break down what I've just kind of gone through. So let's say you have some dipoles. These are my magnetic atoms, and in any configuration, we have no trap. What do they want to do? Well, they want to align themselves head to tail. This is their energy minimum configuration with no dropping potential or anything. And then this causes a collapse because they want to pull together. And then you end up with some nice self-bound droplet in free space, which is just balanced from all of these different attractive and repulsive interactions. And then you add some confinement. So you squash it along this long axis. And now it costs too much energy to remain in this long droplet, and instead it makes a series of smaller droplets, still minimizing its energy, still keeping as many atoms as possible head to tail, but also having some side. Now you've got these other droplets side by side proportion. And then, so this is basically the experiment from Till and Faust showing the last slide. But then with some careful tuning of the parameters, you can allow the density to touch each other, and now you can have global phase coherence. And this is basically the dipolar supersolid. So this is what was seen by 3 groups 2 years ago now, where you have all of these basically mini dipoles, all of your atoms, your dysprosium atoms in the superfluid state, but they also have this density oscillation purely from the balance of these interactions. So you have this broken translational symmetry, which is your crystal, and you have broken gauge symmetry, which is your phase and coherence. So here you can see by changing the scattering length, you can go through phases which are BEC. You reduce your scattering length, you get to this supersolid phase, but you reduce it further, and you go to this independent droplet regime where you don't have these droplets talking to each other. Okay, so this is basically what was done before. So I hope this part's clear. Obviously, got any questions, and shoot in the chat. What I'm going to be talking about relies some modeling of the Grosjeski equation, which you'll probably be very familiar with, but this has got its own special name. It's the extended Grosjeski equation, because it includes these dipole-dipole interactions and this quantum fluctuation contribution. So everything we talk about is a harmonic trap, which can have completely different parameters, different trapping frequencies in X, Y, Z. But crucially, you have this final sort of short-range interaction term, which depends on mod psi cubed. And it's this higher order energy, which is what higher order density, which is what kicks in at the high densities. And we'll also be linearizing when the ground state obtained by this equation in order to look at the excitation spectrum. But I'll go into more details of that when it becomes relevant. So, okay, everyone, well, by now people know that in a linear 1D chain, you can have the supersolid, and this is what, up until this year, has only been seen experimentally, everything's been in 1D. So this is the ground state configuration for these parameters, more down here. The rest are going to change, that's why there's a separation. And we want to know what happens when you go to 2D. And so the first thing you might try is just reducing your Y trapping frequency. In this case, the Y is this way, and that's labeled in the next slide. And what happens, well, you loosen your trap, but we're not changing any of the other parameters. You can see that you go to sort of these 2-row crystals, the droplet number's decreasing. So you've got a fixed atom number, right? So as you increase the sort of area your trap encompasses, the density decreases, and then you go now into just a pure BEC where you have some roton minimum, most likely, but it doesn't touch 0. And so you don't have this crystal. So our idea was, well, let's just increase the atom number proportionally to how we decrease Fy, right? So if we do this, so now atom number's increasing such that the product of Fy and N is fixed, then you can see that actually you always maintain this supersolidity. So you always have the same sort of density-density connection. And actually, this is a really nice way of going from 1D to 2D and staying in the same phase, which is something that hasn't been done before. So our kind of key idea here is that we're going to keep this product of N, Fx, Fy constant, and we assume that this means we'll always be in either the BC phase, the supersolid phase, the independent droplet phase, if we wanted to be in that phase. I'm going to call this the trap density. And the reason for this is you can think of the condensate, from the Thomas Fermi analysis, the condensate radii scale as 1 over the trap frequency. So you could define some volume as the product of these radii, which would just be 1 over Fx, Fy, Fz, and therefore a density will be N divided by that, which is exactly what this is. So we don't include Fz here, and that's only because we haven't really investigated what happens when you change Fz. We expect this still to hold for different values of Fz, but it's safer to just say that we're going to keep this product fixed. One thing we know will change when you change Fz is, like I said earlier, the interdroplet spacing, this roton minimum, is dependent on 1 over the harmonic length Lz. And so if we did vary Fz, you're going to change the actual crystal structure. So it's not 100% guaranteed that this would continue to hold if you had the full product of Fx, Fy, Fz. Okay, so but this is a really nice point. So what we want to do is we want to explore more parameters, not just this one set I've showed you here. But with the GPE, it can be quite hard. It take a long time to get these ground states. So we introduced this new variational model where we assume our wave function can be written as a product of 2 functions. So you can basically, for the moment, just ignore the prefactor, but this is an exponential to rho, your radial coordinate, to some power r, and a corresponding z profile exponential to z to the r. And this is really nice because when you have z is 2, obviously this is just then a Gaussian. But if you have z greater than 2, the profile starts to look like this flat top potential shown here. And this is exactly what you expect from a quantum droplet, from the Bose droplets and the dipolar droplets. They all have this, require this flat top potential. And so by taking the exponent as some variational parameter, substituting this ansatz into the Grosjeski energy functional, we can then minimize over these variational parameters. And I'm not going to show you the full equations and details, I think it's a bit pointless. But essentially we have the single droplet energy, which contains all the contributions inside the droplet, so the confluctuations and dipole interactions, all the stuff. You get a contribution from the XY position of where these droplets are in your trap, in your harmonic trap. And then you get a contribution from the interaction between 2 droplets. which essentially scales again as 1 over RQ for the distance of whichever two droplets you're considering. And the whole energy is the sum over all droplets, right? And so we're minimizing this quantity for an array of droplets. So our inputs are the total atom number and the total number of droplets. And maybe we repeat this process for different total droplet numbers, and we find what minimum configuration, what minimum energy you get for which droplet number. So just to show some examples, here's the same figure I showed before, but on the right now is the same solutions you get from using this variational ansatz. So one thing you'll notice is missing immediately, right, is the halo, which is what the name we give to this, to the ring of atoms around the supersolid. This seems to give a small difference in the expected positions, because obviously the halo itself has some contribution to the positions, to repulsive interaction. It forces them slightly further together, closer together. But otherwise, it seems to work really well. You get, especially some of these like 19 droplet crystals are really nice. And the actual shape and size of the droplets themselves is very closely related to the GPE results. So this is just, I think it's actually inside this crystal here. You can see the variational profile nicely matches the GPE one. So now we have this this method that we can crank the handle over. Let's do this, I think, somewhere 25,000 times over many different contributions. So we're going to look at varying the aspect ratio. So on the left is more 1D, on the right is perfectly circular, and varying the atom number in our droplets. But what's crucial about this diagram is that everywhere has a fixed trap density. So if I'm moving from left to right, and then all I'm doing is changing fx and fy accordingly, such that I have this aspect ratio I require. If I'm moving from top to bottom, then I have to be also changing fx, fy, such that the product n fx, fy stays the same. And the only reason we want to do this is, well, one, to explore this idea of trap density, but also we assume that we'll always be in the supersolid phase, and so therefore our crystal variational model will always be appropriate. And so here's some nice examples. So the color represents the number of droplets, right, in the energy minimum configuration. So as you kind of move from 1D to 2D, I think basically because of the scaling we have, right, because as we're moving, we have to change the trap frequencies and the atom number. So this is why maybe there's some gradient in where the region of constant droplet number changes. But what's nice is as soon as you get to this zigzag phase, which is sort of defined sort of like something like this, we have two rows that as you move across this way, you basically remain constant as the droplet number. This sort of breaks down right as you get to very circular. This is because you have these very well-defined energy minimum configurations where you might have like a hexagon, or you have to have this sort of triangular, almost like Abrikosov lattice configuration. And so actually you'll find that there's big jumps. I think here it goes from 4 to 7 because then in a 4 you just have like a square, but in the 7 configuration you have a hexagon. You have 1 in the center, and you have 6 around. Yes. And there's no energy minimum configuration for a nice triangular lattice with 5 or 6 droplets. Okay, so so now we have found circular supersolids, we believe, right? We should be able to find, by knowing and understanding the left-hand side, which we do, we should hopefully be able to find and understand the solutions for the right-hand side. And this is what we want to work towards. So let's go back to the Grosjeski equation, and let's try preparing a 2D supersolid. So this is quite well known that this is how most of the groups, actually all 3 groups, did this for the first supersolids. They take your BC phase, so you have a high scattering length, and then you reduce the scattering length to pass through this roton transition, this roton instability. So for a linear chain of droplets. This is maybe what you would expect, so maybe I should give a few more details of simulation. So we start with a zero temperature BC, but we add on some non-interacting thermal noise from just single particle harmonic oscillator states, which should attribute to about 30 nanokelvin of noise. We let this evolve like 20 milliseconds to thermalize. Over the next 30 milliseconds, we reduce the scattering length from 95 to 88 A0. So it's going from this EDD parameter I mentioned before, from like 1.2 to 1.4. So it goes through this transition. And then we just let it evolve and we'll just watch. So this is kind of a 3D isosurface of the density. Here's a 2D column density. And here's the phase. And so what we'd like is the phase to be of a uniform color, because this then shows phase coherence everywhere. So I'll just let this go again. So scattering mixture up here, you start to see when it starts to decrease as it gets to about 88. Almost instantaneously, all of these droplets appear at the same time. There's some small phase gradients. You can see there's some oscillations, some collective excitations. And this is what the ground state should look like for 88 E0. You can kind of see, I think there's 6 here. So there's maybe 7 here. So it's slightly excited. And I think as time goes on, it does find its home back at 6 droplets. But there's some nice dynamics. And I'll show an actual measure of this soon, but actually this is a very phase coherent solution. But now let's do the exact same thing for 2D. So we're just going to open our trap and increase our atom number. So, and then this should be our ground state configurations, familiar 19 droplet crystal we've seen a few times. And what's different here is the droplets appear in the middle. And it's also kind of this crazy disco going on. There's lots of jumps of colors between the droplets. But also, it never really looks like it has 19 droplets nicely cleanly, right? There are times where it really resembles this, and then one droplet gets absorbed in the halo, another comes out from the other side. It's a really cool dynamics, actually. But it's really nice to sort of go through almost frame by frame for the actual formation. You start to see one droplet appearing, and then there's a few more. And then there's almost this non-linear wave that's just radiating out. And as this wave propagates through, it starts to get another droplet, then another droplet, another droplet. Whereas in the 1D case, it's almost instantaneous, right? You can see there's a few here, but already, even when it's not so clear here, there's already high density, low density bit, high density, even out in the wings of the condensate. Whereas really that's not the case at all here. There's so much we do just still BC. So we can analyze this a bit better by looking at the excitation spectrum for the BC just above the roton instability. So obviously this is a trapped system, so we have discrete, we have a discrete energy spectrum, and we have some finite width at K, because K is not a good quantum number for a trapped system. We've implemented some finite width in energy just to make it look a bit better, really. It's not an infinitesimally thin line, but also to be a bit more reminiscent of what you would see if you were testing this experimentally. And then so here, just these last 5 modes down in this roton finger, and we've plotted what the density looks like. So you know when you do these perturbations, those are familiar with BDG, Fourier-Legendre theory. You have these 2 functions u and v, and you can plot their spatial extent by plotting u plus u star plus v star multiplied by the absolute value of the ground state solution. And this is what these are showing here. And so you have these different angular roton modes. This is what's kind of unique about 2D, right? So you have these circular modes with the lowest energy, and then you have 2, and you double and go through these symmetries. So for example, if you were to just somehow excite this m equals 2 roton mode, your ground state density would start to look like this, and you'd have this nice density oscillation in your ground state solution. And so you kind of compare this to some of the frames from this simulation, and you can kind of see the very beginning, you have this roton, which you could quite clearly label as this, I'm going to call this an m equals 0 for its symmetry roton mode. And then after that, you can't really link these roton modes anymore to the subsequent dynamics, because you're diagonalizing this ground state unperturbed density to obtain the spectrum. This spectrum is no longer relevant as soon as you have these density oscillations. So this roton mode in 1D seems to really, you have one very nicely described wavelength that almost happens instantaneously, appears instantaneously across your system. And in 1D, you have one mode, creates your crystal, and then there's some heating. And so I would define this as almost like a second order phase transition. So the change in energy between the BEC and the supersolid phase is very small. So when you jump from one phase to the other, there's not much excess energy pumped into giving oscillations. Whereas here, this is telling me that this is a first order phase transition. And so you have a huge jump in energy, and that excess energy is just causing these huge collective excitations in your crystal. And the fact that, yes, you can maybe point out some individual roton modes, but as soon as you get to further time, it's then completely unrelated to the roton at all. I should say we've plotted here is the dynamic structure factor, which was the same thing I showed earlier from the experimental results. So a darker color means there will be a greater response to a perturbation of this wavelength and this energy. Okay, so also in the experiment from Innsbruck, the first supersolid experiments from a few years ago, they also created the supersolid by directly evaporatively cooling into the supersolid state. And this gave a supersolid which had a much longer lifetime. And so we're going to try and simulate this idea by doing some stochastic Grosjeski theory. So if you're not particularly familiar with this equation, really don't worry about it. It's essentially the Grosjeski equation, but you also have some damping term and you have some thermal noise. And so, but with this equation, you can simulate evaporative cooling. So you start with no atoms in your wave function psi, or just a random thermal field, and then you quench your temperature, and you watch as the particle number increases, and you go and you create your BEC, or in this case, your supersolid. So we've chosen parameters. There's a recent paper, again from the group here, called The Birth, Life, and Death of a Supersolid. And they have lots of plots, nice plots that show how the atom number changes, the condensate atom number changes when you directly evaporatively cool into this state. So we can choose our parameters to try and match that as closely as possible, match the experimental result as close as possible, which is why I very carefully use the word, which I think I've spelled wrong. I have phenomenologically introduced the stochastic EGP, so by which I mean, we haven't done the full microscopic derivation to prove that this stochastic GPE should still hold for when you have the dipolar term. But it does seem to match reality when you compare it to the linear chain experiments they've done here. So it gives us some confidence that this actually should hold. And here's just an example simulation. So now what's different is we have fixed scattering length at 88 A0. So again, it's what we should expect for our final solution. But we changed the temperature from very hot, just thermal cloud, and we quench down through the BEC, through the transition to BEC. And the three panels are exactly the same, but it's just different data. So as we get to a certain low enough temperature, so this is the temperature imposed by the noise, but it's not necessarily the temperature of the BEC. That's still got to cool down and equilibrate. You can see that these droplets kind of appear more uniformly rather than some high energy nonlinear wave. and the droplet chamber is changing, but at some point soon, the configuration reaches some nice, about here you can see the 19 droplets. I think there actually were 19 droplets a lot earlier, but then they kind of go in and out of existence in maybe a similar way. But from now on, it's all very clean, right? And there's some nice evidence of vortices going around the outside. You can see from the phase, but the phase has been very uniformly colored for a while. So we have some inkling maybe that if you evaporatively cool into the 2D state, you avoid this first order phase transition, and you should be able to create a nice 2D dipolar supersolid, which will hopefully have a crystal that sits fairly still. So if you did this in the experiment, you might be able to average over many runs with the same crystal configuration. So just to quantify this sort of phase incoherence slightly better, actually I have just a couple of, so you can start to see it's not doing this m equals 0 roton that appears in the center. There really are droplets that appear at random as this kind of uniform crystal growth, which is really nice. So yeah, we're not crossing this transition. So we do make some effort to quantify this phase coherence through this quantity here. So what this is really saying is that you have some phase, 2D phase field, phi, and it's saying for each point in space, how far away is that from the mean value? You have something that's perfectly phase coherent, the same value everywhere, then this is obviously going to be 0, right? But this is weighted by the density. And so then we're kind of ignoring, the areas outside of the droplets, and we're ignoring the really low density areas between the droplets where there's going to be some thermal fluctuations. But this is sort of a density weighted measure of phase coherence for this 2D system. So 0 is a perfect phase coherence, and 1 is fully incoherent, which I think would be basically impossible to obtain. But so what's quite nice about this measure is, you can approximate it as a percentage incoherent, right? So we're going to apply it to this data, which is just the data I've just shown you, but colored slightly differently. So for the interaction quench, these are the density isosurfaces, but the color here actually tells you what phase is. So you can see that as the colors are different, there's actually a phase gradient across the system. And so during this interaction quench, you end up with some droplets that have completely different phase to their surroundings. And evaporative cooling, well, of course, you have a crazy thermal cloud, and you have just colors everywhere, and then you start to have these regions, these mosaic regions that grow with phase coherence, this sort of Kibble-Zurek idea. And you clearly, to have this sort of phase pattern, you have to have some vortices trapped inside the system, but eventually everything nicely smooths out, and you have something which is basically one uniform color. So we repeat these numerical simulations I've shown you 5 times for every data set. Have I been talking for 47 minutes? Apologies. Okay, I'll speed up. And when you go through the quench for the linear chain, you have very little change from 0. When you go through for the pancake quench, you go up to like sort of 70% incoherence. And for the evaporative cooling, it's just continuously decreasing as you're going to some thermal equilibrium. Time equals 0 here we define for when each simulation first shows 19 droplets. Because it's a bit hard to define a t equals 0 between the 3. But this is the fairest way. So a final kind of key point. If you evaporatively cool down to supersolid, you don't go through the first order transition, and you can have some fixed droplet number, which is really important for observation. Okay, some nice experiment stuff. Please just stop me when I run out of time. So here's an in situ image of a dipolar supersolid in 1D. So they have some crossed optical dipole traps. To see this, to get this sort of to have this little cigar trapping, you can change the width of this beam. You can change the aspect ratio. So this is what they did in a recent paper, which is soon to be appear in Nature. This is kind of just before I got here. And they increase the aspect ratio to become more 2D. but also the atom number increases, but they weren't really meaning to do this. I think it's just the way the evaporative cooling happens. You've got a wider ball, and more atoms can fall inside it. So this was all done before this idea of trap density was really thought about. But you can really nicely see that you can go to this sort of zigzag transition. So this is, if you want more details on that, then check out that paper. But after this paper, they added a third laser. They love lasers, experimentalists. And now they can have like a perfectly round trap. And so here is the first ever round supersolid obtained by directly evaporatively cooling into the supersolid state. And here's just the EGPE ground state with the same parameters. So we expect this Super 7 droplet state. The halo is just too low density for them to observe in situ with the amount of noise they have for these pictures. When you do a time of flight, you get something that looks like this. And so you have clear structure, right? You have central droplet and you have 6 peaks around the outside. And this matches what we expect in a Fourier transform of the ground state. You have 1 peak and 6, and there's actually more peaks going all the way around. And probably infinitely, but with lower amplitude. So, okay, so the one that disappears. I'm just going to keep going until you stop me. It's previously, so I've talked about the excitation spectrum for a BC, this is on the left. As you go to a supersolid, you actually get this roton minimum touches 0, and then you get something that has this crystal structure where you can now kind of think about there's Bravis lattices, etc. And you also have this separate free particle branch. So this is where you really have the superfluid and crystal behavior in one. And if you keep going down its scattering length, you end up with just this repeating trajectory with no free particle-like behavior. And so this is already known. This is nothing new from 1D. I don't know why this disappears, but the highest amplitude modes from the supersolid part are given by these Goldstone modes. So an in-phase Goldstone mode is just what everyone knows from a cone mode, where you have the whole superfluid that oscillates at the trap frequency. But an out-of-phase Goldstone mode is interesting and is unique to this system in that you have the crystal oscillates one way whilst the superfluid oscillates the other way, such that the center of mass is 0. And because of this, is a very low energy, excitation. But is these dark red points in the middle 2 plots is essentially dominated by this out-phase Goldstone mode. Okay, great. I have no idea what time it is. Oh, fine. Okay, so this is going to appear again. So we find a way, so if you have these plots up here and you integrate over energy, and obviously these are just 1D, you integrate over energy, you get something that looks like this on the left, right? So this is now in KX and KY space. You have the Goldstone modes, which are shining up nice and red. This is obviously for a linear chain. And for the first time, we sort of look at what happens if you have this in 2D. And it's a bit more interesting because now you don't have just excitations along one dimension. Instead, you have these spacing. Actually, it looks a bit like the momentum distribution, right, from the exponential image for this 2D case. I'm going to a bit more details about this in a second, but this is hard. This is really hard. This is like maybe about half a terabyte of data in this one plot, because you have 512 BDG modes, all of them in 3D with like 512 cubed points or something, to be able to create a graph which is correct up to this ellipse in K-space. So you can do this test where does this integral multiplied by omega equal h bar squared k squared over 2m? If yes, then you're inside the ellipse. If no, we're outside the ellipse. And this is the F-sum rule. So yeah, this is a lot of effort. But to look at some of these excitations, some of the interesting ones, you have this rotational mode, this rotational Goldstone mode, where because it has this is a circular trap, so there's no specific orientation, so you have some zero energy mode, it just will spin. You have this out of phase Goldstone mode, where all the droplets are going one way and the superfluid's going the other way. You have something that resembles a quadrupole mode, so if there's little arrows going red, then you've got 2 droplets going out and 4 going in. And you have some other cool surface crystal excitations where 3 are going in, 3 are going out. We also do some excitations of the positions for the variational model, and you can see these exact same modes. And it's interesting because it's a lot easier to do this for the variational model. It's not so computationally expensive, a bit more analytically hard. But it means you could then apply these same ideas to, let's say, like the 19 droplet case, and you can get some cool excitations. For example, all these droplets are going one way whilst the outer row is going the other way. There's some really nice excitations. And so, yeah, putting in the time and effort to do this for the variational model should hopefully be a lot easier than having to do this for the GP. Anyway, right. So in 1D, if you have the roton wavelength equal to the interdroplet spacing, this is the scenario you need for this continuous phase transition. But we can see from this that that's not what's happening here. So if you just draw some lines between the droplets in kx or in x space, then you have some wavelength which are defined 2 by the kx, and that actually corresponds to exactly this point. So it's not the interdroplet spacing, but it's like the spacing in XY space. It's these Bragg planes that's causing this spacing. And for example, just along x equals 0, you can draw the same thing between lines in Y, and then this is how you obtain this point. Actually, if you try and find where is the interdroplet spacing, it's in these black circles all the way around. So there's basically no weighting from the BDG at the interdroplet spacing wavelengths. And this might go some way to explaining why there's so much heating when you pass through this transition. Okay, so summarize. We've talked about a lot, but yeah, so these large excited crystals can be found via an interaction quench, but they don't really have a constant droplet number. So instead, we developed this stochastic theory to model this evaporative cooling method, and we did this in experiments, and we also found a really nice round supersolid, and all of the information from sort of this part of the talk should be appearing in a paper which is being submitted tomorrow. And then the other parts on the variational model and this idea of trap density explored in a lot more detail will be appearing in another paper, which is also done, but we're just waiting for that one first. So yeah, so if you want more details, and go to those. In the future, we now have 2D supersolids, so you want to look at vortices, right? So this is kind of the phase profile for a vortex in a supersolid. You also have some really interesting ground states in 2D. This is like a honeycomb lattice where the high density is here and the low density is in the middle. And you also have like high density rings. This is an interesting phenomena. I should thank people I've worked with, more people at Innsbruck and Luis Santos, Germany. I've forgotten what university is Hanover. And I really need to mention that there's lots of positions. This is really weird. I didn't realize this was here, but it was on the website for the group. My face has been photoshopped onto a dipole. And this is basically everyone who's here at the moment. But there are theory positions, experimental positions in both PhD and postdoc open at the moment. So if you're interested in coming, email Francesca. So thanks very much.
Thanks very much, Tom. So the webinar is competing with Sky News for breaking news. So does anyone have a question? Albert?
Yes, I have a question, Tom.
Hey.
It's a question I always had about, and it's regarding the true nature behind the transition between the supersolid regime and the droplet phase.
Mm-hmm.
I mean,
sorry, what was your question?
Which which is exactly the because if I understood correctly, when you get kind of incoherent droplets, it's as a not as an equilibrated state or as a ground state, but as a result of kind of a Kibble-Zurek mechanism because of the quench of the scattering length, right?
Mhm.
While if when you reduce the temperature by using a stochastic GPE, you never get incoherent droplets at long times.
I think you do if you go to lower enough scattering length. So the ground state from the GPE, yes, you will always get a phase coherent solution because you're looking for a real wave function, right? But as soon as you take this ground state, for example, shown in here, as soon as you take this this solution, then run it into the real-time GPE. Actually, each droplet has its own chemical potential and therefore its own phase winding. So you have, e to the I.
But
U
is
to,
this temperature dependent then, or not?
no. So that will happen even with a zero temperature GPE.
Yeah, but the point is that if you use zero temperature GPE, I mean, how would you make sure that you got the proper independent droplet phase if you if you do a simulation at sufficiently long times?
I mean, you're right to be questioning it because, yeah, I think for the independent droplet regime, you probably shouldn't trust GPE results because, yeah, you really should have probably some wave function for each droplet.
Yeah, I mean that's why my question is really this transition between the supersolid and the droplet is really a transition. It's a crossover, or it's just the same phase.
But the
Just the
GPE,
droplet,
but the
just an asymptotic.
GPE, yeah, the GPE does give each droplet a separate phase though if you run in real time. So as much as I wouldn't be inclined to trust the results, and for the stochastic stuff, we never went as low a scattering length to look at independent droplets, and there can be a separation even in the stochastic, even in the GPE, there can be a separation between two droplets that allow their phases to wind independently. So at least the expected behavior can still exist in that theory, even if I agree with you that that maybe the results shouldn't be trusted wholeheartedly. I mean, there's a discrepancy between theory and experiment anyway. Like there's about a couple of Bohr radii difference between where these transitions lie. And the quantifications term, which I didn't really mention too much about, even that must be wrong somehow by a small amount because there's some imaginary contribution which we just conveniently throw away. So it's certainly not perfect, but it does seem to match the experiments so far. And all the stuff I've done is really has ignored the independent droplet case.
Yeah. Okay. And then I had a second question too, because when I've well, you mentioned in the last slide or in the second to last that these works from Aarhus in the group of Thomas Paul.
Yep.
I've been always very concerned about how can these weird geometries exist, because for instance when I did simulations and you do you always get a triangular lattice of peaks, of density peaks, and according to Thomas Paul you can obtain these at very high densities, right? I wanted to ask you if you are not really at that densities, or you could
So thanks for asking. Here's my backup slide. If you take the trap density argument and you go in reverse, so you tighten the radial trapping, you actually can see these sorts of effects they see in the works of Thomas Paul, and there was another recent one by Tillman Fow's group. So you take a BC, instead go the other way, right? You increase the radial trapping, you go through the triangular lattice, you keep increasing the radial trapping, you go to some strange droplet configuration, and then you get to something that looks kind of like, maybe it's like 3 droplets connected. And so this sort of state so we try to stick to experimentally relevant parameters here, right? So I think what goes with your question is that actually the density doesn't increase that much because the droplet density is fixed, right? Obviously it has this flat top potential. You keep on adding atoms, it just gets bigger. So actually the density doesn't increase, but what increases is let's say the amount of area that has that level of density. In the experiment, the 3-body losses are huge for these densities, which is why there's a much shorter lifetime for the supersolid states than there is for the BEC. So I think that these states are observable in experiment. Particularly these ones are a bit smaller, because here the density is probably no higher than if you had, let's say, 1, 2, 3, 4, like 8 to 10 droplets. The density is certainly no larger. There's just more of it at that density. And here's a cool ring droplet state or something. I think these are perfectly observable. It's just it's maybe not even for necessarily shorter lifetimes, but it's just finding the right parameters.
Yeah, but then in order to observe them, at least in the experiment, apparently it's just a matter of making the system smaller.
Yeah, I think so, because if you look at the papers you mentioned, they have, in order to see their version of these things, these honeycomb states, etc., they have like 10 to the 6 atoms, or they have kilohertz of trapping frequency. So maybe this is what's quite nice about this idea is that you can here, this is still about 100 hertz in each dimension, and only 10 to the 5, maybe to nearly 10 to the 5 atoms. I didn't put the parameters. So I think you will be able to see these things hopefully soon, but they're going to be small. They're not going to be these, big honeycomb structures.
Yeah, sure.
But great question. Yeah.
Okay. Just as a curiosity, is Francesca planning to go into that direction or not? Well, not really.
I think I'd be shot for saying. I'll keep. This is fine to talk about because it's been published tomorrow, but I think everything else. I think there's idea. I think there's a lot of other easier things on the horizon.
Okay.
To give a nice cryptic answer.
Okay. Understood. Thanks.
I think Samuli had.
Sorry, I was chuntering away, muted. Yep, Samuli, you're next.
Yes. All right. Thanks. I was going to ask you. I think you mentioned this in passing already, but so if you take a supersolid and rotate it, supposedly you're going to get some sort of vortices. Could you elaborate on that a little bit?
Yeah, actually, the guy who's asking last question, Zelba, has very well poised. He's got some nice papers on rotating a supersolid gas. Yes, so in similar to BC, you end up with vortices that like to sit between the droplets. Maybe the challenge is rotating the BEC perhaps experimentally. But you in the same way you should be able to observe vortices, and their lattice structures may be a bit more complicated because they're a bit more pinned by this effective potential of their neighboring droplets. There's another more recent paper, actually it might be this paper here, where they discussed vortex-vortex interaction, but they only looked at sort of 2 opposite signs. And it seems that even in the 0 temperature GPE, that these vortices almost like seek each other out and annihilate each other. Even if I think in this whole homogeneous solution which they were considering, I think without the supersolid crystal, they should just oscillate around each other indefinitely. So there's certainly some interesting phenomena. I mean, for me, what's going to be hard is seeing it, right? It's already in the zero density region. So you look at this, you look at maybe there's actually a vortex there, right? There's zero density. It's how do you define this fluctuation compared to I mean, there's probably not, because it doesn't. Something would appear in the interference pattern with a single vortex, but averaged over many serializations, it's hard to say. But yeah, I think yes. The short answer is yes. If you can rotate your BC, there will be vortices in supersolid phase.
All right. Well, one of the reasons why I'm asking is we've done some experiments in superfluid helium-3, which placed inside an aerogel made from rods, basically. And so this gives you, well, it's not as ordered, but basically the idea is that you've got like rods along which there is no superfluid, and then the vortices have to be in between. And these rods, they pin the vortices, and then the resulting, well, non-dynamics, if you wish, of vortices is very different from what you get from bulk. What you get in bulk helium, as an example. So I was interested to hear how it would work here.
Yeah, I mean, there's so I don't know if it's clear from this picture I've stolen from these guys, but like I think as well from this paper, or maybe even Albert's paper, the droplets aren't pinned, right? The droplets are free to move, and so you have actually some evidence of a counter rotation where the droplets are trying to maintain phase with each other, and so they maybe start going the other way to try and negate just the overall velocity field is zero for them, and they have this phase coherence across the entire droplets.
Yeah, all right, thanks.
Yeah. Rob.
Yeah, great. Thanks, Tom, for a nice talk.
Hi.
And hello. Yeah, just had a question about if I understood correctly, as you sort of simulate the cooling down, so your temperature quench, as it were, then you go, in a sense, directly from the sort of thermal state into the supersolid state. Could you imagine a sort of a parameter space where you sort of go through a BC phase and then into the supersolid, or will it always be direct? Do you have a sort of feeling on that?
I think you would, yes. I think even maybe, I don't know if you do here, but like if you, I kind of want to look at this, look at the figure from this paper. I mean, maybe this doesn't give you the best idea for the simulation, I'd hope, but like, so here you look at the formation in the experiment, right? And then there's some sort of unmodulated density, but then is this just a thermal cloud? And you can, so I think because so in the simulation, you have a few free parameters, right? You have this parameter gamma that links the coupling between the thermal cloud and your the above cutoff atoms. So in this thermal bath, you have your BC or C field. If this was a very small parameter, there'll be a very slow growth, and perhaps then you would go through BC, and then slowly your atom would increase, and you would maybe have to pass through this transition. So perhaps it's it's certainly something which deserves a lot more effort and work than what's just been presented here to investigate what happens. But it seems that if it happens fast enough, then you have more of this uniform ability. But I would guess that, yeah, if you go slow enough, if gamma is small enough, that I think you would maybe go through BC first.
But then, think sort of the equilibrium phase diagram has the two separate, or is that what you're?
Yeah, but then so also kind of going back to reality. So it's like so in this work they actually looked at several different quenches, right? So they had because you have your fast quenches, and they also had, which was 100 milliseconds, and then they had slower quenches for 500 milliseconds for the temperature. And in both cases, they ended up with a nice coherent supersolid. I don't think it made that much difference. I think, but also if there were one doubt, I think it'd be interesting. But obviously, it'd be very different in 2D. You go much faster. You're going to have Kibble-Zirek, and you're going to have vortices. I have seen some simulations. So so for this sort of diagram, obviously this black curve goes down. But I think if you include simulations where you create a single vortex, then this really shoots up, right? This because it's suddenly by this measure it's phase incoherent. So there's going to be I think there's more to the story than maybe what's been presented, but we chose this ramp to match basically the ramp they do in the experiment, and that seems to be the right speed to ignore the transition.
So it's somewhat an open question still, I guess, but yeah. Okay.
Yeah.
Great, thanks.
Cool.
Thanks very much, Tom. I think that's everything. I think you can retire. So just to say, and just to advertise, we've got our final webinar before we go on a summer break in 2 weeks' time, where Callie Wilson will be giving a talk, and details will be emailed out in due course. So thanks very much again, Tom, for giving today's talk, and thanks very much for everyone for coming along.
Thanks. See you soon.
Thank you. See ya.
Bye.